This is Jingfeng. I'm a visiting research scientist at the Ruohan EIP and of the Imperfect Information Learning team under Professor Suyama. Today, we are really happy and very honored to have our guest, Professor Ruohan Zhan from Hong Kong. She right now is an assistant professor at the Hong Kong University of Science and Technology. Her research developed a method to innovate data-driven decision making using tools from causal inference, statistics, machine learning, with interest in problems from platform operations and economics. Previously, Ruohan received her bachelor degree from Peking University and a master degree and PhD in Stanford. So let's us hugely welcome Ruohan to give us her talk today, post-episodic reinforcement learning inference. Welcome. Ruohan, please get started.
Thank you. Thank you so much for the very nice introduction and also for having me here, Suyama and Jingfeng, for organizing this amazing seminar. Today I'm going to talk about if we have some data that has been collected by the episodic reinforcement learning agent and how we can estimate and make inference, which means that we construct confidence intervals around our estimation using the data. This is a joint work with my wonderful collaborator, Vasilis from Stanford, and this is still an ongoing project. So if any of you have any questions or feedback or comments during my talk or after my talk, feel free to just mention or reach out. We would really love to incorporate your feedback into our version later. Yeah, just as I mentioned, feel free to interrupt me if you have any question during the talk. Okay. So let's talk about the data format first. So what do we mean by the episodic reinforcement learning data? And it can be more generally framed as the dynamic treatment regime. It means that the data is collected in an episodic manner. For each unit or each individual, we roll out, and the agent will roll out an episode or a trajectory. During the episode, the agent will apply action or treatment on the same unit or individual for multiple stages, for multiple times. And in the end, the unit will output an outcome and something the agent is interested in optimizing. So consider and this has many applications in different domains. For example, in e-commerce, like during digital marketing, the platform wants to attract new customers and convert them into some loyal customers. And when a customer arrives, the platform wants to know how to convert her into some loyal customer, and the platform may apply different treatments such as the advertisement or the coupon or customer service. And in the end, the platform is really interested in whether what is the conversion rate here. So when the platform has collected some data from its production system, it is interested in evaluating what is the efficacy or what is the treatment effect of the different treatments on the final outcome, which is the conversion rate. So here the different treatments represent, for example, the advertisement or the coupon and the customer service. Okay, so with that, the platform can assign different credits to the different marketing strategies, such that the company can better budget funding towards different strategies in the next round. And this also has some application in clinical trials, which actually has been studied a lot in literature and also in practice. And in those scenarios, a patient will receive multiple rounds of the treatment. and the doctor or the practitioner is very interested in what is the patient's physical health condition after the whole clinical trial trajectory. To put it more mathematically, we have a policy pi that is used by the agent to assign the treatment over the L stages. And at the first stage, the agent will observe a context or an initial state x1 from some population distribution px. Here we assume that the environment is stationary, which means that the px is fixed. And then at each stage j, the treatment or action tj is assigned based on the current state or current context xj. And this treatment or the action tj will transit the xj to the next state or next context xj plus 1. And in the end, we'll observe the final outcome y here, okay, which is a function of the last state and the last action. So here I will mainly focus on the Markovian setting, but our framework can also be adapted to the non-Markovian setting. So with that, we can talk a little bit more about the outcome here. So what does potential outcome mean here? It means that under a treatment assignment sequence, T1 to TL, what is the outcome? Like what is the Y which we may observe? And similarly, we can define the conditional potential outcome, which is conditioning on the current context Sj at the stage J here. And then it becomes something maybe many of you guys are familiar with, which is the value function definition. That is exactly the potential outcome, like expected potential outcome if the treatment is assigned according to this policy pi here. And similarly, you can define the Q value function that is conditioning on the current stages context xj, and also we may assign an action or a tau here, and the future treatments will be assigned based on policy pi. And this is then also is defined with this in expectation. So the underlying assumption that is very essential to almost all of the estimation or inference problems here is the unconfoundedness assumption, or here it is termed as the sequential conditional exogenate assumption, which is essentially the unconfoundedness assumption in the sequential setting here. It says that, okay, conditional on the current state Sj, the future treatment, so this is Sj is the current state. For the future potential treatment assignment, the future potential outcome is independent of the current treatment assignment. So no matter what you assign, like at the current state, but there are different trajectories in the future, if you have a different treatment assignment path, and then those outcomes will not be affected by your current treatment here. So maybe so here is the assumption here. As I mentioned, it's essentially the unconfounded assumption in the sequential setting. And with that, we can define our value function or Q function. So maybe here is a more graphical illustration about the assumption here. So it says that, so here we consider two stages. There are only two stages here, and binary outcomes. Essentially, conceptually, there are four different paths for the treatment assignment, and there are four different potential outcomes here, which are the y00, y01, y10, and y11. Okay, and but in reality, you can only in practice we can only choose one path to assign our treatment. For example, here it is the y01. So at the first stage, we'll assign the treatment 0, and at the second stage, we'll assign treatment 1. And we observe the y01. And the sequential conditional heterogeneity assumption essentially says that we observe the y01, but this will not affect the other the values of other three potential outcomes, like the y00, y10, and y1 here. So it basically says that we fully capture there's no unobserved confounder in our DGP data generating process. For the so in order to do make progress, and we impose a little bit of assumption here about the data generating process. So here we follow the literature, like which is common in biostats, and now it's more and more common in the econometrics, which is the structural mean lasting mean model. For this kind of modeling, we have the belief function definition here, which basically is a difference between the Q value function. So this is the X stage J. We assign the treatment tau, and how is this treatment tau? How does this treatment tau compare with the now treatment, the treatment 0 here? And this is exactly what the belief function tries to capture. It's actually essentially the same for the advantage definition in reinforcement learning, which just tries to evaluate the effect of an action as compared to some baseline action. So here the baseline action is 0, and we use a Q value function to the difference of a Q value function, which we term as a belief function, to evaluate it. And this will give us a very handful characterization of the Q value function and also our value function pi here. So suppose we have some data, some sequence of data, like episodic data that has been collected by some behavior policy pi now. And then the Q value function for alternative policy pi can be reformulated in this way here. And then our the value function, or the policy value of the target policy pi, can also be represented in this expectation way. Okay. So
what is capital Y in the lemma?
Y is the final outcome we observe.
A final outcome. Okay.
Yeah. So so here we only consider that the final outcome is something we try to evaluate, but I understand in reinforcement learning we will have some intermediate outcome which can also help us to refine our estimation. Yeah.
Okay, thank you.
Yeah, thank you for your question. Okay, with that, so the first assumption, the second assumption, like a very essential assumption we are trying to impose here is a linear belief function assumption, which basically says that the advantage or the belief function can be represented in some linear way for some known feature mapping by J here. So if we have this notation, then the Q function or the value function can be written in a very concise way. Here, like the theta J is essentially the treatment effect of the at stage J, and the phi J again we call here phi J is the feature mapping we know of the current state and current action. So you may think this is restrictive, and I agree, but actually it can, even if the belief function is nonlinear, and we can use some kernel approximation and kernel regression to try to approximate it. And later on, we will show that in our simulation, even the model is misspecified, even the belief function is not linear, and we can use some polynomial approximation to help us to reduce the estimation error as compared to some baseline method.
Hi, Professor Ruohan.
Yeah.
I'm sorry to interrupt you, but I have a question that for the bleak function, it basically means the advantage function in reinforcement learning, right? And in your definition, the baseline function Q, maybe with the action of 0. So what's the meaning of that 0? It means do nothing, or it has some.
So exactly.
Yeah,
it means do
that's why.
nothing. It means
do
do
nothing.
nothing. Right. So something we want to evaluate is that, okay, if we really apply the treatment, how does that compare to something if we just do nothing?
Okay, I see.
Like,
thank you.
What is the baseline effect here? Yeah. Thank you
Okay,
for your question.
thank you.
So I think, for example, in the medical setting, the doctor wants to understand if the drug or the treatment really help the patient, and also in some like e-commerce setting, the company wants to understand if the strategy really helps to convert to the customers, or if the customer will just be converted naturally, like something. This kind of effect or the uplift is something we will try to capture here. So I give you, so here is a more concrete example of the data generating process that satisfies our previous two assumptions. The Markovian model here basically says that, okay, if the state transition dynamics are linear, then this kind of the DGP satisfies the assumptions we just mentioned. Okay. Finally, we finish our setting for our data generating process, and then we introduce our estimation goal here. So we have some data collected sequentially by some RL agent. So for unit I, we collect we have the agent use the policy pi I to collect the episode I. And the pi is potentially updated based on the current information the agent has observed so far. So which means that the episode for the unit I is likely to be collected depending on what the previous episodes have told the agent. And we have this, so under our previous assumption, we have this very nice and concise formulation. That is the firstly the positive value or the theta null here, which is the value of the target policy we want to evaluate, can be represented in this linear way. And the theta j here is the stage-wise treatment effect. Like theta j and phi j, some feature mapping. We assume that we know beforehand. Okay, so let's talk about okay. Sorry. The goal here is to estimate the theta j. The theta j and the theta null. Estimate means something we want to estimate. So the treatment effect and positive value are the things we want to estimate using the data collected. And how do we do the estimation? It's kind of like a recursive pooling or dynamic programming. Suppose we have a data from the unit I, that is xi1, which represents the initial state. ti1 is the first treatment, and then xi2, and so on and so forth. And yi is the observed outcome, final outcome for the unit I. Okay, so we firstly try to estimate what is the theta L, which is the treatment effect on the last stage L. And we have, based on our previous lemma, we have this very nice formulation, like we have this moment equation here. And we have used this moment equation to form a Z estimator and to estimate our theta L, which is quite standard. And then once we estimate the theta j recursively I suppose from theta L to theta L minus 1 and to theta 1 to theta 0 here. So for example, for the stage J, suppose we have already estimated the theta J plus 1 to theta L. And then we have this second moment equation here. Essentially will help us to identify what is the theta J here. So this moment equation will involve the theta J plus 1 to theta L, but recall that we have already estimated the theta J plus 1 to theta L, which are the later stages treatment effect. And then we can use those estimations to help us to estimate the theta J. Okay, so it's kind of like the dynamic programming or the recursive pruning, as I mentioned. We start from the very last stage, and then we move backwards to estimate, and finally to reach our initial, reach our positive value estimation data. Okay, so with that, but this estimation can be improved. For the previous formulation, we can identify the theta J using the theta J plus 1 to theta L as a nuisance parameter. Nuisance means that those parameters will help us to estimate our theta J, our main estimation theta J here. So this is a nuisance estimation. But as you can imagine, if the estimation error of the future, of a later stages treatment effect, will back propagate to our estimation of the theta J, right? And this error can accumulate over time. So to deal with that, essentially it says that, okay, so at stage J, we want to estimate theta J, and then the later on treatment effect will be used as a nuisance estimation parameter. To deal with that, for the estimation with the nuisance, we can follow the double machine learning or the semi-parametric literature, which help us to construct this kind of a orthogonalized moment equation. So we modify the previous moment equation a little bit by multiplying it with the TJ, the center TJ, TJI minus its expectation, conditional expectation, and you can verify that this is still mean 0. By orthogonalization, I mean that the estimation with this orthogonalized moment equation, one can show that the estimation error of the nuisance, the theta J plus 1 to theta L, will only have the second order effect on our current estimating theta J. And this is very useful since this will help us to construct have a faster rate as well as construct the inference result, which is a CLT essentially, basically. So in that way, the estimation error of the later on treatment effect will not affect much on our current stages estimation. Okay, so with this moment equation, MJ orthogonalized moment equation, we very naturally we have a natural Z estimation here. That is we use the empirical mean, and then we solve this moment equation, and then we have some our estimate theta hat. So if we under the overlap condition, which essentially controls the amount of exploration at the stage J for the unit I. So the covariance here is the how much the agent is willing to explore as compared to exploiting the current information. And if we have this overlap condition or the amount of the exploration condition, we have that our theta J can be estimated with this rate here. And we call it L is the horizon of the episode or the length of the trajectory.
Yeah, in the previous slide, actually, I wanted to ask, so if L is large, do you suffer? And then actually the answer is yes. Yeah?
Sorry,
I wanted to ask, so if L is large, then does the error accumulate? And so the algorithm suffers a lot.
Yeah, exactly. So because here we really depend on the later stages estimation to estimate our current stages of the parameter, and if we have a very large L, then as you can imagine, the errors from the later on stage treatment effect will back propagate and will accumulate. And it also reflects in our error rate here. Like if L is very large, which essentially has a higher, which essentially imposes a stronger assumption on the exploration or on overlap. So the alpha needs to be small. And for the IIT, like if in the IIT setting, like if the agent does not update her data collection policy, then the L will be 0, which is there's no adaptivity at all. But if you allow the agent to update the policy along the way, but if L is very large, there's very little room the agent can be adaptive since yeah.
I see. So in practice, so what kind of L are you considering?
What kind of L I'm considering? Okay, it depends. It really depends on the application. I think. So for example, for the digital marketing example, I mentioned previously, with something we are really trying to do right now. We only evaluate a very few, like less than 10, like maybe less than 5 marketing strategies, and for those strategies, yeah, it's fine. But if you really consider an infinite horizon, I would say this is okay. This is very difficult. Or if you can impose different alpha j, like alpha j for different stage j, and here will allow the summation of alpha j needs to be finite, like needs to converge. Essentially, it means that for a later stage, you will explore less and less, and yeah.
Okay, thank you.
Yeah, thank you for the question. And I just want to interpret the result a little bit more. So if for the last stage, as Sugiyama, or like for last stage, we have this estimation rate, but for the first stage, we have a much slower estimation rate, as Sugiyama just mentioned. This is because although the data is generated from theta 1 to theta L, like from the first stage to the last stage, but our estimation is conducted like in a recursive, in a backward direction. So we estimate theta L first, and then and finally we estimate theta 1. So the error will back propagate to the early stages treatment effect. Yeah, let's just want to emphasize a little bit more about being adaptive here. So if we allow for a larger amount of the adaptivity, then the reinforcement learning agent will collect data like and update the data collection policy pi I along the experiment, which means that the pi I is updated based on the previous I-1 episodes. And presumably we assume that exploration will be less and less, and with more and more information, the agent will exploit what she has collected so far. Yeah, and this really makes the overlap condition, like the condition we just mentioned, worse over time. So essentially, this is the covariance or variance of treatment assignment, like uncertainty. We impose there for each treatment assignment as J for the unit I. If I is very large, then we allow essentially this can be close to 0, but we still in order for our estimation to still be statistically justified, and we really need this exploration to be maintained at a certain amount, which is the I to the power minus alpha here. So look, now the question is that, okay, can we improve our estimate a little bit more such that we can get a faster rate, and eventually we want to get the inference result? Yeah, so the answer is, of course, yes, we can. Otherwise, I would not be here. So recall that the overlap condition is becoming worse over time due to adaptivity. But we can apply adaptive ways to like counter effect this kind of the reduced exploration. And essentially here we'll apply the root of the inverse of the covariance with the hope to standardize our estimate here. So for example, we can apply the with here covariance, like root of the covariance inverse, and then we can get a faster rate as compared to our previous one. So recall there's a two factor here in the previous one, the very naive unweighted version. But if we apply the weight here, then we can have a faster convergence rate. Okay. And as the title suggested, the goal here is to really to do inference, which is that we want to estimate not only we want to estimate our parameters, but also we want to construct the confidence intervals around our estimation, such that we can say with statistical significance how large our estimation value is. So following a very if we have a certain assumption and using a martingale CLT, essentially since the data is generated sequentially and this follows a martingale pattern, and we can have a we can apply martingale CLT to show that our estimate is asymptotically normal. We can have a single martingale CLT, and this part is kind of standard, but we still cannot do inference. Why is that? The CLT, so because if a data is collected adaptively, we have no control on whether or not the data collection policy or the pi will converge. So it may not converge. In that case, we're not. So if we just simply invert the Bn, the normalization matrix Bn here, it is not valid. So we cannot use this Gaussian to approximate our estimation error. But this is not the case for the IID setting. So if a data is collected by some fixed policy, the Bn will converge to the Bn is essentially some empirical mean, and it will converge to its population mean, which is the expectation. And there's no problem there. But here, since we allow for the agent being adaptive, like the agent has the freedom to adjust the data collection policy. So we really don't want to impose the assumption the convergence of the data collection policy. It might happen that during some time the agent figures out, okay, one treatment is better than the others, but when the agent collects more and more data, it figures out, okay, another treatment is actually better. And if the signal to noise ratio is really small, and it's very likely if you run the trials for multiple times, every time it will give you a different final policy, a convergence policy, which is likely. So here we don't want to assume the policy, the data collection policy, to converge, which implies that our BN may not converge. So a single CLT does not really satisfy our requirement to do inference. But so how do we deal with that? We need some stronger result, which is type of if for those of you who are familiar with the barrier estimate bound, this is exactly the thing we want to achieve here. So basically, it says that okay, for the CLT, the left-hand side, the standardized statistic, we have a distribution for that. We have some distribution for that, and for the right-hand side is the standard normal, right? And the barrier estimate bound essentially tries to quantify the distance between these two distributions, and also tries to quantify how fast these two distribution come closer to each other. This is kind of the distributional convergence we try to achieve here, and this will give us the strong Gaussian approximation result. So okay, but to be able to achieve this result, we need to have a more delicately designed weight, and I omit here for but feel free to check our paper. We have a very detailed description on how to construct those weights here. Again, suppose that we have the overlap condition and consider the partial linear Markovian model. Then for any convex set A, we have this barrier estimate bound. So which means that the left-hand side, the standardized statistic, belongs to this convex set A. The probability of that happen, minus the probability of the standard normal, belongs to the convex set A, can be upper bounded, can be uniformly actually upper bounded by something. This is also a finite sample result, which is really impressive, I think. Essentially says that no matter for any convex set, you can do that. If we have this one, we can invert our BM even if it is not converging. So with that, we can use this standard this normal distribution with the mean zero and the variance to be the BN inverse times the BN inverse transpose to approximate the distribution of our estimation error here. And so if you want to do estimate the confidence interval, construct confidence interval of any projection of the data, for example, what is the theta j, like the treatment effect on the stage j, the theta j here, and you can simply invert, you can simply apply it to construct the confidence interval, and more we can also, if you want to construct a confidence region around our estimate, and we can also have this one, confidence region here. Those approaches are kind of standard for the inference. Okay, some simulation results. The first slide here is to demonstrate that our inferential result is really valid. So here we consider partial linear Markovian model, and to make the problem a little bit more difficult, we consider that we'll also use the lasso setting. So which means that our context or our stage can be in a high dimensional space, and the state transition can also but the state transition essentially follows the lasso pattern, like some sparse signal will affect the next state. And then we consider two stages here. So for each stage, the parameter is in a two-dimensional space, and plus the positive value. Essentially, we want to estimate 5 parameters here. We compare different estimation methods. The blue line here is the naive estimate, which means that we do not apply any weighting strategy here. The orange line here is the consistent weight we just mentioned previously, and the green line, maybe this is covered by the red line, but the green line here is the oracle line, which means that we know exactly what is the data generation process, and we can get some perfect way to stabilize our estimation. And the red line here is our proposed method. Like we estimate the parameter from the data, and we just really follow the exact procedure we give in our algorithm, and construct our confidence interval and construct our estimation. And as you can see that we really have a nominal coverage. The nominal coverage is 90%, and both the oracle weighting and our strategy can recover, can have this nominal coverage result, but for other two weightings, we don't really have those kind of performance. And the second set of the simulations demonstrate the robustness. I just mentioned previously, like when I introduced the linear belief function, okay, although we assume the belief function to be linear, this will allow us to have a really nice formulation of the policy value, and will help us to estimate our policy value like recursively. But it's possible, like we specified our model, like and here in particular we use the nonlinear belief function model here, which is the and then as I also mentioned previously, we can use some approximation like the color regression to approximate this nonlinear belief function. So here I use the polynomial approximation, and we can have a different degree here. So the green line here is given by our estimator on the MSE of the policy value. So here the structural parameter or the treatment effect does not really have any meaning since the model is misspecified, but we can still use that to estimate our policy value. So the green line is given by our method shows that we really have a much smaller mean square error as compared to if we do not apply any weights to stabilize our estimation. With that, I think I can end my talk here. The takeaway message here is that okay, for the episodic reinforcement learning, we introduce some structure like the structure mean nesting model to model the whole data generating process. And in order to estimate the policy value, we introduce the belief function, where at each stage the structure parameter is the treatment effect. And we apply this kind of like recursive pooling or dynamic programming to estimate our policy treatment effect, and finally on our policy value. And then we use some adaptive weighting to stabilize the estimation variance due to the whole data generation process to be adaptive, and we can achieve faster rate. And for the inference result, we can apply a more delicately designed weighting scheme such that we can achieve this kind of the strong Gaussian approximation, which allows us to construct confidence intervals around any projection of our parameter, or to construct the confidence region about our parameter. And finally, even the model is misspecified. Even the model is not like it's not linear, and we can still use color regression method, which will help us to have a better estimation of the policy value we want to estimate. Yeah, that's pretty much all of my presentation, and I'm happy to answer any question you may have and comment you may have.
Oh, thank you so much for the talk. So in the beginning of your talk, you talk about the unconfounding assumption. So I'm wondering, where do that assumption come into play in the analysis?
Oh, okay. So You're saying you're talking about this assumption, right? This unconfoundedness assumption here. So I would say everything is built upon this assumption. So we it basically says that your current treatment will not affect your alternative estimation. So essentially, what we're doing here is that we have some data collected by some behavior policy, and we want to use that to infer the value of another policy, right? And if the unconfounded assumption is not satisfied, if it is violated, and it's very possible. So there's no identification. Like we cannot use the data from one policy to infer another policy since the pattern is changed and the functional form is changed. Like everything is changed here. So this is I think this is a very standard assumption. If you want, especially we want to construct this kind of a value function or Q value function here. I'm not sure if I answered your question, but yeah, let me know if you have any feedback here.
Yes, it answers my question. So you suggest just the Markov decision. Markov decision process is not enough. In order to make some justifiable reasoning, we need additional assumption, for example, the unconfounding assumption here, right?
So the Markovian assumption, I think these are two different assumptions. The Markovian assumption says that, okay, the current state can summarize all of the information you have received so far, right? And the policy is assigned based on current state, and the state transition is determined based on current state, right? Is that that is the, correct me if I was wrong here. And the sequential conditional extraordinarity assumption or the unconfounded assumption is that no matter which action you apply at the current state, like think about there are a lot of the parallel universes. In one universe, you take one path, but this will not affect the result in other universes if you take different paths.
So does this not guarantee under the conventional MDP setting? No?
This is not guarantee on conventional MDP setting.
So excuse me. I understand why you need to use the unconfounding assumption to guarantee the current university will not affect the other university, right?
Yeah.
And I'm wondering why the conventional MDP formulation cannot capture this requirement. Because MDP also provide a way to evolve multiple universes, right? So this is my question.
I think MDP is kind of used to summarize the past information in a nice way, but it does not say something about the future information. So the MDP is like conditional on current summarization.
I see.
The future is independent of the past. Like how you reach the current state does not matter. As long as you reach the current state, then the future does not depend on the past.
I see. So you suggest the conventional MDP only capture the history, but for the future, you need this unconfounding assumption.
Yeah.
I see.
I think, yeah.
So
basically, I think
more feeling about it. Thank you so much.
Thanks. So I think this condition can be violated. For example, if some unobserved confounder can affect how likely you receive a treatment, as well as the outcome, and if this information is not captured, then this assumption will be violated. So basically, we assume that everything that will affect the outcome at the current state will be observed. Otherwise, along with the treatment will be observed.
Thank you.
Yeah.
Thanks again for Ruohan's great talks. Thank you for your contributions to Recon.